Taking a look at last night's homework on page 175, we had two questions, and different people requested us going over both of these questions. So we'll look at both of them. Question number one says a loonie of mass 7 grams is taped to the top of a toonie of mass 7.3 grams. In other words, we have a mass here of 14.3 grams. The fact that one is 7 and one is 7.3 doesn't really matter. Okay, what matters is that we've got two objects that are really combined as one that have a mass of 14.3 grams. The incline is 30.0 degrees. Okay, this is pretty straightforward so far. We've got a couple of forces acting on this loonie-toonie system. There's a force of gravity acting down. That's m times g, or 0.0143 kilograms times 9.81. We also have a normal force acting at 90 degrees here. So the normal force is going to act something like this. The resultant force, the combined force of gravity and the normal force, is going to look like this, right?
No, it's not.
All right, so what's it look like then? Yeah, if it's going to be perpendicular to the normal force, then we should draw that normal force a little bit shorter, and it's going to look something like this. Okay, we have to have our 90-degree angle in there between the normal force and the resultant vector. In other words, this red force right here that we're calling FH should be parallel to the hill. And in fact, it is the force of the hill that drives it down. We're going to redraw it. We're going to draw it up there against the hill so that we can see on our object, see that force a little bit clearer. Really, it's the same thing, but it's a little bit clearer if we draw it up there at the top. Do we have friction here? We do. It stays at rest. Force of static friction is going to act backwards. Now in the end here, if this is at rest, we know that the force of the hill is going to be equal to static friction, otherwise it wouldn't be at rest. If FH was bigger, it would accelerate down the hill. If FF was bigger, it would accelerate up the hill. Well, that can't happen, right? So these two forces have got to balance each other out. In other words, if we find FH, then we're going to automatically find the force of static friction. We know that this angle right here is 30 degrees because it's always the same as the angle of the hill. We're looking for the opposite side of the triangle. So we're going to say sine 30 degrees is equal to opposite over hypotenuse, which is 0.0143 times 9.81. We're going to multiply those numbers together and then multiply it by sine 30 to get the value of FH, which, of course, for us, is going to be the same value as the force of friction. Multiply those together, I assume that we end up getting 7.0 times 10 to the negative 2. Is that right?
Wait, is gravity negative or not?
That's a good question. Is gravity negative or no? Gravity is negative. Gravity is always a negative force. But when we're dealing with it here, we make it positive because the force of the hill
Interruption in grade 12, A to M, that are
is an absolute value. So when we're doing this trigonometry, we're not finding a direction of the force of the hill. We already know that, right? It's parallel to the hill, down the hill. We're finding an absolute value. Because of that, we're going to use the absolute value of gravity as well. So although it is technically a negative force, a downward force, when we're doing this, we're going to take the absolute value of it. In other words, make it a positive number. Okay, it's a good question. Yep.
I got 7.34.
Anybody else get 7.34? Anybody else get 7.0? 7.0? Okay, just check that work record. Check it on your calculator. Okay, 7.0 times 10 to the negative 2 is the force of the hill, but of course that's got to be the force of static friction as well. If it's at rest, if it's not moving, then those two forces have to balance. Travis? Yep. Okay, let's take a look at number 2 now. A loonie of mass 7 grams is placed on the surface of a rough book. Force of static friction of 4.4 times 10 to the negative 2 acts on the coin. What's the maximum angle at which the book can be inclined before the loonie begins to slide? I seem to like the loonie questions here. I think our example was a loonie question yesterday, and both of these questions are. Here's the book on an incline. Okay, we want to find this angle at which this book will begin, or this loonie will begin to move. The loonie has a mass of 7.00 grams, which is 0.007 kilograms. We have a force of friction, force of static friction acting on it, of 4.40 times 10 to the negative 2 newtons. In fact, that will be the maximum force of static friction, because we're told that's the force of static friction that's acting on it. That's the maximum force of static friction before it's going to begin to move. So 4.4 times 10 to the negative 2 is FSF max. We also know that we have a force of the hill straight down. We have a force, the normal force acting at 90 degrees. And then the force of the hill, which is gravity and the normal force combined. So we draw that force of the hill right here. And now let's find its value. Or can we find its value? Can we find its value? We don't know what this angle is right here, right? We know it's theta, whatever the angle is right there, but without knowing what theta is, we have no way of finding FH, do we? Josh? Yeah. Yeah. Okay. Just before it begins to move, these two forces have to balance. Therefore, FH must be the same value as the max force of static friction. So we're going to say it's 4.40 times 10 to the negative 2. So this time we're going to work backwards. Instead of saying sine theta or sine 30 degrees or whatever the angle is equal to opposite over hypotenuse, we're going to say sine theta is equal to opposite that we actually have the value of this time over the hypotenuse. Right, usually we have this value, we're solving for this value. This time we have this value, we're solving for this value. So how do we find theta now? On your calculators, Wayne, go ahead. Okay, so let's first go sine theta is equal to whatever this number is. Wayne, what do you have for that? 0.641. Okay, now we're going to go theta is equal to the inverse sine, just like the inverse tan that we've done before, right? Of 0.641. And when we do that, we should get 39.8 degrees. Okay. I think I mentioned in class one day when we were talking about static friction and kinetic friction and so on that sometimes when I come home from school, as soon as I walk into the front door of my house, there's the banister that goes upstairs, and it's this wooden banister, or at least the top of it's this wooden banister. Sometimes I take my phone out of my pocket. I've got a bunch of stuff in my pockets, and I'm trying to take my jacket off and whatever. I take my phone and I set it on this banister, and it's on this angle, like this. I set my phone there, and it stays there. And I know it's going to stay there because I've done it before. Okay. The case that I have on my phone has kind of a rubberized back. Okay, when that rubberized back is against that wooden wooden banister, then it sticks. It's because the coefficient of static friction between the rubber and the oak is high enough that it's going to stick. Okay. You can imagine now how we could go back and find the value of the coefficient of friction pretty easily. Right? We're doing essentially the analysis that we've just done there. We can measure the angle of that incline. We can measure this angle of the oak banister right here, get its value, go back to the normal force, okay, set the force of friction equal to mu times the normal force, calculate the normal force, find the force of friction, okay, and then calculate the coefficient of friction from that. Okay? So, for those of you who ever thought physics didn't have any real-life applications, there you go. Now you go home, and boy, doesn't everybody want to know the coefficient of friction between their OtterBox case and the banister? Doesn't everybody want to know that? All right. Maybe they do. Maybe they do, yeah. All right. Here's another one. Here's another one. A 50-kilogram toboggan is on a snowy hill. The hill forms an angle of at least 20 degrees with the horizontal. The toboggan just begins to slide downhill. In other words, if it's under 20 degrees, okay, static friction is big enough that it can hold it. If it's above 20 degrees, static friction isn't big enough to hold it. We want to find the coefficient of static friction for the toboggan on the snow. This is essentially what we were just talking about, isn't it? This is almost exactly putting the OtterBox on the banister and finding the coefficient of friction. If you're at a little bit of a loss as to how to find the coefficient of friction from this problem right now, that's okay, because we always have a place to start with these. No matter whether we're trying to find coefficient of friction or acceleration or whatever, we always start with this, a free body diagram. Okay, there's a 50 kilogram sled here. There's a force of gravity acting down and a normal force acting at 90 degrees. The angle that we have there is 20 degrees. The angle that we have here would be 20 degrees because it's always the same value. The normal force and the force of gravity combined at 90 degrees there gives me FH. That's the force of the hill pulling the sled down. There is also, however, a force of friction going back this way. And it's going to be static friction because the sled isn't moving until the end of the problem. We can do that. Anybody can do that, right? We don't have to know how to find the coefficient of friction to do that. Just before it begins to move, what do we know about the force of the hill and the max force of static friction? This thing's at rest. Look up here. This thing's at rest. It's not moving. What do we know about the net force when it's not moving? Okay, here's the sled. Look at the sled here. Okay, it's not moving. This is the force of the hill pulling it down. Okay, the force of friction pushes it up. What do we know about those two forces if this sled isn't moving? They've got to be balanced. They're equal and opposite. They've got to cancel each other out. So let's say when we're at that max angle, just before it begins to move, let's say that the magnitude of the force of the hill will be equal to the magnitude of the force of static friction. Now, we can get the force of the hill. We can say sine 20 degrees is equal to FH, that's the opposite side of the triangle, over 50 times 9.81. Okay, let's get that value. 50 times 9.81 times sine 20. You get 167.76. Okay, that's the force of the hill, but that's also the force of static friction. In fact, that's the maximum possible force of static friction. But we know the max possible force of static friction is equal to mu times the normal force. If we want to find mu, given the force of static friction, we also need to be given the normal force. So let's find it. The normal force is the adjacent side of that triangle. Let's say cosine 20 degrees is equal to adjacent over hypotenuse, 50 times 9.81. Let's get that number now. 50 times 9.81 times cosine 20 degrees this time. 460.92. All right, we're almost done. We've got Fn. We've got the value of the force of the hill, which is the same value as the force of static friction. Let's rearrange this and solve for it now. Let's say mu is equal to FSF over Fn. So in this case, it's going to be 167.76 divided by 460.92. We do that, we should get 0.36. Anybody else get that? 0.36. What are the units for that, by the way? Newtons divided by newtons cancels, and we have no units. So 0.36. Okay? So remember, if you're having a little bit of trouble with something like this, okay, whether it's this problem or any other problem, Start off by drawing a diagram. Start off by drawing the free body diagram. That's what we did in the beginning there. Fg, Fn, Fh, and then we said FSF, the force of static friction. Then we had to recognize that Fh was equal to the force of static friction because it wasn't moving. Then we calculated the value of Fh right over here, which gave us the value of FSF max because Fh is equal to FSF max. Then we calculated the normal force, and we put it in right here. Given this one and this one, we were able to solve for this one, which is exactly what we were looking for. Problem done. Yep. All right. Let's see what we can do with these two.